Okay, on problem 1, it says we have a random sample of 50 men who've been with the firm between 10 and 15 years. 36 have made partner. So what we have is whether or not they made partner. So that's going to be a categorical variable, something to do with proportions. But then there's another random sample of 50, and of those 40 had made partner. So what we have is a PA and a PB, the difference between two proportions. So I said in the first group, which I'll call group A, we have X is 36 and N is 50. Out of 50, 36 had made partner. And in group B, 40 out of 50. So we can get the sample proportions. 36 out of 50 is 0.72. And 40 out of 50 for P hat B is going to be 0.8. And I'm going to go ahead and I know when I get to the critical value approach that I'm going to have the pooling also. So I'm going to pool these and say I have 76 out of 100. So P bar is going to be 0.76. So when you have two proportions, now I went ahead and pooled because I'm going to do critical value and P value. I don't need that for the confidence interval, but I have that down. The first thing I would do, personally, and you may see this in some of the keys that I put up, I've been trying to show on the very top of the sheet on my keys, at least the ones I did yesterday, I go ahead and use my calculator to get all the check figures straight away. So I'm going to go to Stat, Test, Two Proportion Z-Test, that's option 6, and I'm just going to put in 36, 50, 40, 50, and I'm going to go ahead and put here, it says difference. So that means it's going to be a two-tailed test, not equal to when I get to the hypothesis. And calculate. So the Z that I am going to calculate, I'm going to show all the work, but it's going to be, or should be, close to about minus 0.94. Minus 0.93658, whatever, 94. And the p-value is going to be about 0.3489, so I'll just say here about 0.35. So if I get outside that range very far, I'll suspect that I've made some kind of calculation error. I'm also going to go ahead and get the confidence interval by doing Stat, Test, and going down to Two Proportion Z interval, which is option B. And let's see, it's going to be a 95% confidence interval, so all I have to do is slide on down there where it says C level, put 95, then go to calculate. And so my confidence interval is going to be about minus 0.2467 to 0.08668 is what they have. Now we won't come up with exactly that when we calculate, but we should be in that ballpark. We'll do a little bit more rounding. Okay, so I think actually I'll start with D. Is the sample size large enough? The sample size is large enough, but it's because 36, 40, 14, which is 50 minus 36, and 10, which is 50 minus 40, all the yeses and nos have to be greater than or equal to 10. Again, if you watch some of my videos from the past, I might have said 5. That's just, the rule for that seems to have been changed over the last few years in most textbooks. The critical value approach. First of all, our HO and HR. HO is that PA is equal to PB, or you can write that PA minus PB is equal to 0. That's really convenient when if you do graph the sampling distribution, because the center of the sampling distribution will be 0. And then since it's two-tailed test, we want to know if there's a difference, just PA not equal to PB. So we will reject HO if the z-test is greater than, and for 05 on a two-tailed test, you should see 1.96. And then we'll just calculate. Z-test is equal to the statistic P hat A minus P hat B minus the hypothesized parameter, which is, again, is always going to be 0 in the problems that we work, divided by the square root of, and remember there are two formulas for standard error when you're dealing with proportions or the difference between proportions. And this one's P bar Q bar times 1 over NA plus 1 over NB. And that's all equal to 0.72 minus 0.8 minus 0. That's from the hypothesis. Divided by the square root of 0.76, 0.24, 1 over 50 plus 1 over 50. I'm going to put it in my calculator, but assuming I had everything entered in my calculator correctly before, this ought to come out to be about minus 0.94, somewhere in that range. And I get minus 0.936, which is about minus 0.94. And that is not greater than 1.96. That is not less than minus 1.96. So we will, I'm just right here, fail to reject HO. And conclude there might not be a difference, that the proportion of males and females that make partner that are within 10 and 15 years of continuous service doesn't differ for males and females. So that's part A. I'm going to go ahead and try and get part B on here because it builds off of this 0.94. So 0.94 means that this value, this difference that I have, this difference of 0.08, 0.72 minus 0.8, is a little less than one standard error away from the center of the distribution. Okay. So we have a distribution with P hat A minus P hat B. We know that the center of that distribution is 0. It's PA minus PB is equal to 0. So in all of the problems that we have, the center of this sampling distribution, this is the sampling distribution assuming HO is true. So as all of them, here's our HO. That's the center of the sampling distribution, labeled with whatever statistic we have that we're looking at. This is the sampling distribution of the difference between two sample proportions. Then we find the actual value of the statistic, which is 0.72 minus 0.78, P hat A minus P hat B. I'll go ahead and write that up here somewhere if I can. Here we go. P hat A minus p hat b for this sample is 0.72 minus 0.8 is equal to minus 0.08. So I'm going to locate down here a difference of minus 0.08. That's what's on this axis. And then p-value is out here, except for we have to keep in mind this is a two-tailed test. And I didn't do it up here, but a lot of times I'll just write somewhere up at the top somewhere two-tailed, just so that I remember when I get down to something like this that I have p-value in both tails. So just you need to keep, when you get to the p-value, make sure that you know whether you have a one or a two-tailed test. And when you have a two-tailed test, the distance from the center to the statistic you observed should be the same distance, or you're going to go the same distance in the other direction. And since that's 0, that's easy to do. We have 0.08. Questions before I erase this? I would just put pause, but yesterday when I did that, it just erased everything automatic. So I think I'll ask if there are any questions before I do that. Okay. Well, we'll find out here. Actually, I think I'm just going to erase everything here and redraw that sampling distribution. And we knew that this was Z equal to minus 0.94. So I'm going to look up in the Z table for 0.94, and that's 3264. That's from here to here. And that means that the area out here is 0.5 minus 0.3264, about 0.1716. That's this area. But we have another 0.1716 over here. So on a two-tailed test, make sure you double that up. And so our total p-value is going to be 0.3432. That's just 1716 plus 1716. So again, I've had the graph again here. First of all, we have this. We're going to reject HO if the p-value is less than 0.05. We have the p-value, I'll just write it down here again, equal 0.3432. That's not less than 0.05. So you fail to reject HO. Same as before, conclude there might not be a difference in the in whether or not they made partner for males and females. So, and I will ask it this way, I meant it when I did this, but I'll be more explicit that I want a conditional statement, an if-then kind of thing, that tells you what the p-value is. And basically, it's just, again, saying that picture, just writing that picture out in words. If PA minus PB is equal to 0, if that's true, then there is a 0.34 3, 4, 3, 2 chance, a p-value chance, that I'm going to put this completely out here, that samples of NA equal NB equal 50. That's just the two sample sizes that we took here. And I'm not as concerned that you put that in there, but I think it might help some of you understand it. That if we took those samples, there's a 3, 4, 3, 2 chance that those samples would yield either, I'm going to have to write this over here. Just follow me over here. Either p hat A minus p hat B less than or equal to minus 0.08. Here's the 0.08 down here. Okay. Or p hat A minus p hat B greater than or equal to 0.08. This part. Okay. So again, once you have the sampling distribution drawn, if HO was true, there's a p-value chance, that's the total area in the tails, that we would either get here or here. I'm going to put this one more way, and if you don't get this, you do. If it helps you understand it better, then fine. You could say that the absolute value of the difference is greater than or equal to 0.08. That would include both tails. That helps you understand that we would be off by more than 0.08. And by off, I mean the difference between the two sample proportions. Questions on this one? You got it? You seem quizzical. Is equal to 0 right here. You could have said if PA is equal to PB. Those are the same thing. You could put that too. Either one that makes more sense to you. Those are, if they're the same, then the difference is 0. But it's always if whatever you had in HO, and remember we stated HO as PA equal to PB, and we also said we could state that as PA minus PB is equal to 0. Those are the population proportions. I'm going to put this back into a picture that we had long ago, except for, well, it's a little bit different. What we have is two populations and two samples. So we have PA and PB, which our hypothesis is that, this is for males and this is for females, that the proportion of promotions are the same in both. That's our hypothesis. But then we go get samples and we get p hats from each one of them. And in this particular case, they differ by 0.08. The chance of that happening, if there isn't a difference in either direction, differing by that much, is 0.3432, the p-value. But keep in mind, all of our hypotheses are about the larger population. You're going to have p's and mu's, or some combination. PA minus PB or mu A minus mu B. Those are the larger population characteristics. But then we'll get the sample information. So this is always if, and this is about the parameter, whatever we have in our hypotheses, then there's a p-value chance that we get statistics this far away from the center of the distribution. I'm going to erase and then do the confidence interval. Okay, so for the confidence interval, this is part C, we're going to have the statistic P hat A minus P hat B, plus or minus standard error, P hat A, Q hat A, NA plus P hat B, Q hat B, NB. I'm going to leave it as is for this, but it would be okay to switch which one's A and which one's B. That would allow you to deal with a positive number for the proportion. I'll leave it like it is for now, but that would be okay too, just to say that it's women are A and men are B. That would be okay too. Well, we had, in our first group, we had 0.72. That was the 36 out of 50. Minus 0.8, that was the 40 out of 50. I'm going to put here minus 0.08, that's just that number. Plus or minus, I don't care which one of those you put on the other side there, but the square root of 0.72, 1 minus that, 0.28, divided by 50. Plus our other proportion, sample proportion was 0.8, 1 minus that, 0.2, over 50. And then we can just put that in our calculator. Oh gosh. I don't know why I'm doing this lately. There has to be the Z value in there too, sorry about that. For 95% confidence, that's 1.96. I'm getting minus 0.247 to 0.087. And I've forgotten what I wrote down a minute ago, and I don't have it here, so I'm going to run that back through my calculator again. Yes. Okay. So minus 247 to positive 0.087, that interval includes the number 0, which would mean no difference. Therefore, there might not be a difference. If 0 was in the interval, there might not be a difference. So now we have the same conclusion in all three. We failed to reject HO, whether it was critical value. Remember, HO was PA equal to PB, or that the difference is 0. We failed to reject that. And also, we can look at the interval that includes 0. Well, if we failed to reject it, that's why. We couldn't reject this possibility that they were the same. I want to remind you, I'm just going to go ahead and say, I'm not going to put any multiple choice on this test, but I do want to have you keep in your mind with confidence intervals that it's a long run concept. That we're talking about that 95%. We're not, this interval either has it or it doesn't, but we're saying is in the long run, if we took many, many intervals, that 95% would include the real difference and 5% wouldn't. So I just kind of want to remind you of that. It's summer school. The final exam's next week. We might as well think of this in part as a review for that as well. Questions on this one? Okay, on this one, what sticks out to me right away, we have a sample, and from that we have a standard deviation. This is going to be some form of t-test. Now I'm going to look to see if there's one sample or two, is it matched? Well, there's one sample of 50 based on bestsellers, and another sample, so we're going to have a two-sample t-test. And so the first thing I want to do is just write down the information from the problem. Two groups. The first one has a sample size of 50, a sample mean of 3.8, a sample standard deviation of 0.7. The second one has 50, 3.4, 1.1. So all I've done so far is just write down the information from the problem. I'm going to go ahead and circle as I'm going through there the word differ, which means that I'm going to have a two-tailed test, which means that when I get to the p-value, I'm looking at both tails, not just one. And with a two-sample t-test, really, from a practical standpoint, the first question you want to ask is, were the variances close enough to be pooled? Don't look at the 0.7 and the 1.1. Those are the standard deviations. You have to get the variances. It's 0.49 and 1.21. And this is more than twice that. Therefore, you cannot pool. Okay? So this is going to be unpooled. Neither variance is greater than or equal twice the other variance. So that means in this case, if we pooled, we could just get the degrees of freedom NA plus NB minus 2. But on the unpooled, there's a huge formula that we're not going to use. So we're just going to put the numbers straight away into our calculator. We'll get check figures anyway, but we'll also be able to get the correct degrees of freedom. So I'm going to go to Stat, Tests, two-samp t-test, and just enter the information from the problem here. I have 3.8. Make sure you put in to your calculator the standard deviations, not the variances. We only computed the variances to decide whether or not we were going to pool. Not equal to, because it's a two-tailed test. No on the pooling. Calculate. And the degrees of freedom there, it says 83.09. Just forget the decimal part. It's just the 83. Always round that down. And so now when we use our t-table, we will go to 83 degrees of freedom. And that's kind of the preliminaries on this one, just to get to now we can start working things out and do our normal stuff of statement hypotheses, critical value, calculate or get a decision rule, calculate the critical value, and so on. Then the same thing with the p-value, and then the confidence interval statistic plus or minus confidence coefficient times standard error. I'm saying that fast, but I want to say what I'm getting at, it's the same thing now. So we'll state the hypotheses. HO is that mu A is equal to mu B. Same thing as saying mu A minus mu B is equal to 0. Either one or both of those is fine. There's some advantage, I think, to thinking of that in both ways. And HO is that the two population means are different. just different. We're going to, I wouldn't normally write this here, but I'm thinking about how much space I have here. Reject HO if t-test is greater than some point or less than minus that same point, since it's a two-tailed test. And I have 0.05 and a two-tailed test, and 83 degrees of freedom, two-tailed 05, 83, 1.989. So now the t-test is going to equal the statistic x bar A minus x bar B minus mu A minus mu B hypothesized over the standard error, which is the square root of s squared A in A plus s squared B in B. And I might as well go ahead and note that my calculator says that's going to be about 2.17. When I cut the degrees of freedom, I already have the answer right there. So I'm going to calculate this, but I'm going to come up with pretty close to 2.17, unless I make a mistake. Been known to happen. 3.8 minus 3.4 minus 0 divided by the square root of the first variance, the 0.49 times the sample size minus 1, that's 49, plus the second variance, the 1.2921. My pen's not working very well right here. Times 49, and all of that, or I'm sorry, that's not right. Good. The first variance, the 49, divided by the sample size of 50 plus the second variance, the 1.21, divided by 50. I get 2.23. Maybe I put something in. You got 2.1? Okay, well that's right. I must have entered something in there wrong. Let me look at that. Oh, okay. I put in 1.12 instead of 1.21. That's why you write the numbers down to begin with. 2.17 about. I should have written those down up here now that I... P-value, I'll go ahead and write is 0.0329. I'll just put 0.33. I'm going to erase it in a minute anyway. I would also, I'm not going to right now because I'm going to erase it anyway. Go ahead and calculate the confidence interval on here and make sure that's right. And that's why I would say write those down. The 2.17 is that would tell me that was a little bit too far off. If I would have been 271 or something like that, but 223 to 217, I thought that might be a little different than rounding. I mean, my numbers are okay over here. I just put 1.12 in my calculator. In some places, that's known as the Roach transformation. You just change numbers in the middle of the problem. That's what that is. Okay, so that's the critical value approach. Now we're going to go to the p-value approach, which we know the p-value is 0.033. And with any of the t-tests, we're just going to use our calculator for that. So, to draw this out, it's x bar A minus x bar B, our curve here. The center of that, mu A minus mu B, is equal to 0. The difference that we observed was 0.4. That was 3.8 minus 3.4. X bar A minus X bar B. So we really just can plot one number. It's the difference, the 0.34. But then with a two-tailed test, we also would go the same distance in the other direction. And assuming you put not equal to, I'll go back and make sure that I did. Yes, when you calculated the t-test, that p-value of 0.033, it's already done the adding. The total area right here, all of this plus this together, the p-value is equal to 0.033. It occurs to me now that I got so excited about my miscalculation, that I didn't state the conclusion or anything in the last part. So I'll go ahead and say it. Well, I'll put it here. We had 2.17. That was greater than 1.989. Therefore, we reject HO, conclude that the ratings do differ for books that are either are or are not based on bestsellers. So anyway, now on to this one. That's just occurred to me. I forgot to write it. Well, anyway, here we're going to reject HO if p-value is less than 0.05. 0.033 is less than 0.05. So again, you'll reject HO, and you will conclude the ratings, at least the average ratings, differ depending on whether or not if you're based on a bestseller. So when you're writing your conclusion, you're basically just going back to the problem. And we're saying, yes, the population mean ratings based on bestsellers differ from the ratings for movies not based on bestsellers. So you can just go make that into, in this case, a statement. They do differ. If you'd failed to reject HO, in other words, just get rid of that, make that a capital, change that into a period, and you've got your conclusion. You can make up new words if you want and put that into meaning, but that's all we're doing is putting this back in to the context of the problem. Questions? Okay, then for the confidence interval, we'll have the statistic x bar A minus x bar B plus or minus confidence coefficient, which is t, times the standard error, s squared A in A plus s squared B in B. And it would have been fine to have already computed x bar A minus x bar B as that. And then have written here x bar A minus x bar B plus or minus t times s x bar A minus x bar B. Those are equivalent formulas. If you're doing the critical value and the confidence interval, it might make some sense to do this. It'll save you a little bit of, if you're putting things in your calculator, a little bit of keystroke changes, I guess. That was 0.4, or 38 minus 34, plus or minus, and for 95% confidence, that was 9.89. And then we had the variances, the 0.49 divided by 50 plus 1.21 divided by 50. And before I plug that all in, I'm going to go to my calculator and stat tests two sample T interval and make sure I have 95. The numbers are all in there. I just put them. And that we have no for the pooling and 0.033.767 about, which makes sense. I know that since I rejected HO, this interval isn't going to include 0, but I'm going to go ahead and just 0.4 minus 1.989 times second square root and I get, that's what I get, 0.33 to 0.767. Now, I'll just tell you, when you're taking the test, I am going to ask that you show the formula. I am going to ask that you show me where you put the numbers. And when you come down to your final calculation, you can do it both ways. But if I had a choice, I would just use the calculator and put the interval right here. If I only had time to do one, just use the stat function. It's going to get it right. But I will have to see that. And then also you would say in this that the entire, well, I'll just put it this way, the interval does not include 0. Therefore, you conclude that there is a difference. Okay, there's one other question here, and that is, what graphs should you draw to support this analysis? So if you're going to actually collect this data, you actually collect it and you had all the data, what graphs would you use to display the data or to do other things? And it's a quantitative variable. So at a very minimum, you ought to have a box plot, a comparative box plot where you have both boxes on there. And maybe a histogram would be appropriate, or a pair of them. So what would I be looking for in a histogram and a box plot? I know we're kind of reviewing and putting some things together here. Okay, so one thing is just to look to see if they're different. That's probably a little easier to see on a box plot than a histogram. So depending how you draw them, you can draw them either way. Let's say that we draw them horizontally. Group A and Group B. And you can look at this and see that it looks like Group A has higher ratings than Group B. So you put them on the same graph. Now, this is median, not mean, but so one purpose of the box plot is just to visualize that whether or not we have a difference. Now, I'm just making up that exact box plot. So that's one thing, is just to look and visualize the data that you have. What other things might you look for? Outliers are extreme values. So let's say that these graphs look like, let's see if I can, no, maybe I don't need to do that. Well, I guess I will draw. What if they look like that? Still looks like A is a little bit more. That's true, maybe not as much. But there's an outlier there. And that could be drawing Group B's average down. Is the sample size large enough for this to be a valid process? Yes. What we're saying is that once our sample size is over 40, our outliers are going to be taken care of because we have a large enough sample. Okay? However, let's say that it looked like you guys can see those over here, extreme values. The sample size isn't large enough. And you can see why. I've kind of drawn these to some kind of, I didn't finish quite with them. If you just look over here, it looks like there's not much difference between the two groups. But because you had some really extreme values down here, it's going to pull the mean down. Okay? If I put the means on here, and sometimes you'll see it might have a little asterisk or something in the box that would denote the mean. The mean here might be here, lower, but it's because of these 2 points. It's not because of most of the data. So that's what we mean by saying that if we don't have a large enough sample size, we kind of invalidate the process. We want to know if there's a difference between the two groups. Well, if we're looking at the means, if all or almost all of that difference is the result of 1 or 2 points down here, then is there really a difference between the two groups? Or you just happen to get an extreme value this time? Or maybe those aren't even, maybe there's something, if it was something over here, you know, like the Bill Gates kind of thing, maybe that shouldn't be in the sample at all. But having those 1 or 2 extreme values down there really makes this, if you're looking at the difference between the two groups, a suspect kind of thing. So 2 reasons for drawing the box plots. One is just to look at these differences. How far do they differ? And what you can look at how spread out they are, but really we're looking at just, do they look like they differ? And then the other thing is you can use them to check for outliers and extreme values. Of course, with a histogram, you can draw those and still have the same kind of comparison. A little harder, easier to see that on a box plot, that the center of this one is higher than the center of that one. But one thing that is, I think, a little bit easier to see on a histogram is if you have skew. Now you can see that on the box plot too. If one tail's a lot longer than the other one, you probably have skew. But it's just a little easier to see on a histogram if you have skew. Okay, so in problem 3, I'm just reading through here. I see the word population proportion, and there's just one sample. This is going to be a 1 proportion z-test. I'm going to go ahead and use my calculator to get some check figures here. X is 27, N is 100. We want to know if we can conclude that the population proportion is less than 0.3. Of course, HO is that it's equal. So I'm going to go to stat test, 1 prop z-test, 0.3 for the hypothesis, then 27 out of 100, and then a less than, because it says less than 0.3, and then calculate, and my z is going to be about minus 0.65, my p-value 0.256, and then I'm going to go stat test 1 prop z interval, option A, and let's see, I'm doing 90% interval, so I'll make sure I have 90 there and calculate. About 0.197 to 0.343. So again, that's just getting really all of my check figures for parts A, B, and C. Then I can calculate and have some confidence. If I calculate them out by hand and I get this, I'm pretty sure I enter all the numbers in correctly and use the right formulas and all of that. D, is the sample size large enough? It is, because 27 say yes and 73 say no. Okay. 27 said yes, so if there were 100 total, that meant 73 said no. Both of those are greater than 10, therefore you have a large enough sample size. So the first problem we had today, 2 proportion, we were looking at all yeses and nos being greater or equal to 10. The second problem we had means. We're using the 15, 40, 100 rule, looking for skew, outliers, and extreme values. Now we're back to a problem with proportions, a categorical variable. We're looking at number of yeses and nos, both greater than 10. So for the critical value approach, I'm going to reject HO if z-test is less than minus 1.645. That's less than, so this will be less than minus. And the z-test will equal the statistic p hat minus the hypothesized parameter divided by the hypothesized proportion 1 minus that, or the hypothesized no, divided by n. Our sample proportion, 0.27, p hat is equal to x over n is 27 out of 100 is 0.27, minus the hypothesized 0.3. And for hypothesis testing, we're going to use that 0.3 here, and 1 minus that, which is 0.7, and divide that by n. So I'm going to check all this out, and I do come up with minus 0.65, which is what I did when I just used the stat function. So I'm feeling like I have this one. That's a good feeling to have. You got the same thing both ways. You can move on now. Minus 0.65 is not less than 1.645. So we fail to reject HO. So the population proportion of people who consider themselves to be mournful people might not be less than 0.3. So it's all of this, but might not be less than 0.3. I'm going to skip to part C, mainly because I just want to get two things up here that we can see both at the same time. The p-value, we would just take that minus 0.65. We'll do it in a minute and put it on the sampling distribution, all of that. But what I want to just reiterate is that when we do the confidence interval, it's p hat, the statistic, plus or minus the confidence coefficient, z, times the standard error, but it's not this standard error. Okay? We use the hypothesized proportion. Hopefully I said p when I did that, and that was just a thing on the board, but make sure that was p there, not mu. For purposes of doing the hypothesis, we assume HO is true, so we use the 0.3 when we calculate our standard error. But when you do a confidence interval, that's not tied to a specific hypothesis. You can use it to test that hypothesis, but it can be used to test other hypotheses as well, or just to get an estimate. So the 0.3 isn't in here at all. What you have is just what you have from the sample, the p hat. Then 1 minus that over n. And so now we have 0.27. For a 90%, that's 1.645. The square root of 0.27, 0.73, divided by 100. If you got those mixed, if you use the 0.27 over here or the 0.3 over here, when you check your calculation, you're not going to get these numbers that we have over here. So that's another way you can, if you come up with a different number, you should question yourself, did I use the right formula there? 0.1969, that's about 0.197, and then 343. So I did get that answer, so I'm pretty sure I have everything in there. If I'm using that to test this interval, I cannot conclude that the population proportion is less than 0.3 because the interval includes numbers greater than 0.3. Okay? The interval, remember on the difference between proportions, the difference between means, and the pair difference, I'm just looking at 0. But when I have either just one mean or one proportion, I have to look at my hypotheses to see which number I'm looking at. This interval includes 0.3. Therefore, P could be 0.3. In fact, come back over here. I should have said P. A better way to put this would have been P could be, it's the same thing, but it's probably a little better to say P could be 0.3. We can't say it's less than, so it could be 0.3. And the same thing here, it could be 0.3 because 0.3 is in the interval. Questions on what's up here? Then okay, our Z was trying to remember here, minus 0.65. And if we have the Z, I might ask you to show all your work in calculating the p-value. So a Z of 0.65, back on the Z table, is 2422. Distribution of sample proportions. Center of the distribution is the hypothesized proportion, which was 0.3. The sample proportion we obtained was 0.27. We just calculated this error to be 2422. So the p-value is what's left out of the tail, or 0.5 minus that, 2578. And on the calculator we had 256. I'm not that concerned about being off by that much. 256, 257. That could just be rounding error, particularly with low Z values where there's more distance there. You're going to get some rounding error. So the p-value equal 0.2578, about 258. We reject the p-value is less than 0.05. P-value of 0.2578 is not less than 0.05. So we fail to reject HO. P could equal 0.3. We could not reject that possibility. If P is equal to 0.3, if HO was true, then there is a 0.2578, about 26% chance, if you want to look at it that way, that we would get p hat less than or equal to 0.27. That's true. This chance of getting that. Technically, and as I've done in some of those, we should say or think when we have samples of size 100. If we had different sample sizes, the width of the curve would change and your probabilities would change. You don't often say that when people say that, but it really is true that it's based on that sample size. Questions? Okay, given where we're at right now, for the remaining problems I have on here, I just kind of want to get you started. And let me do, on the problems that I put on here, I've put everything on every problem. But on the exam, like if we came to this problem, I might ask you to do the confidence interval approach. And only the confidence interval approach for this problem. And on another one, I might say, just do the p-value approach. On another one, just do the critical value approach. So on the review, I'm kind of putting everything on there. The test will be a little bit shorter because I'm not going to ask everything on every problem. So anyway, for these last few, I want to just kind of go through and make sure that we have what to look for in the problem and what kind of problem it is. Well, on this one, as soon as you see something like after minus before, pre-test, post-test, game over, this is matched pairs. Okay? If you just realize that these two numbers are from the same person, there's just one sample of size 6. Really what matters is the change. Okay? And that's going to be X and so on. I'm not going to do it now, but make sure you could compute and show your work for the mean and the standard deviation where that required as part of the problem. It may or may not be, but if you need to review that, do so. So that's the main thing on this one is matched pairs. And our hypothesis is, does the number of ideas go up? So does this X go up? So your HA is going to be mu greater than 0. Okay, so for the matched pairs, we'll always have 0 there. From then, it's just a regular old one-sample t-test. Your t-test is going to be the statistic minus the hypothesized parameter over the standard error, SX bar, where S is equal to, SX bar is equal to S divided by the square root of N. And then, of course, the confidence interval X bar plus or minus T times SX bar. P-value, we'll use our calculator. All the t-tests, we'll use the calculator to get the p-value. Sample size, N is equal to 6. That means we must be sampling from a population that is at least close to normally distributed. No skew, no outliers, no extreme values. In reality, very seldom would you use a sample size this small. The reason we use sample sizes this small in here is if you're going to do calculations by hand, or even if you're just going to put a bunch of numbers in your calculator during an exam, we don't want to have 100 numbers. So we can see what's going with this, but if I'm running a test on something, my sample sizes, generally speaking, are going to be quite a bit larger than this. There are some practical times when you wouldn't want to have large sample sizes anyway. If you were making something, you wouldn't want to check all of your product. You want to spend most of your time actually producing something. If this were something involving crash testing cars, you don't want a large sample size. Because, every time you crash a car, it costs you a lot of money. So there are financial considerations as well. That's really all I want to say about that one, just to kind of get you in the general direction here. I really put the problems on proportions at the beginning of the thing on purpose because I thought that was the thing where people might need the most help. So in the next one here, had a sample of 8 days. Rita's issued the number of tickets here during the lunch hour, because Rita's the meter maid. Come on, guys. You've heard that song, right? The Beatles? Okay, well, anyway. There's a song, it's on the album Revolver, about Rita the meter maid. But anyway, so is this enough to conclude that the population mean is under 15? There's one sample t-test. So here it says to use your stat function to get the appropriate statistics. That just means put those numbers into list 1, or wherever you want to put them, stat calc, one variable statistics, and then you'll get your mean and your standard deviation. Then you can proceed just like we have in other problems. By the way, you can also do the t-test straight from there. If you have these numbers in list 1, then you could just do stat, test, t-test, and make sure you select input data, and then you just tell the data that you have the data in list 1, and then you could do that. Let's actually, we've got a little bit of time here. Let's put those numbers in your calculator and do stat, edit, and I'm just going to put these in list 1. There will be at least one problem, maybe 2 on this test, where I allow you to use your calculator at full power. That is, you could put these numbers in here, and maybe I would say just use your stat function to get the critical value and the p-value, and don't worry about showing work or anything. So let me make sure I have these in here right. Okay, so now I'm going to do, for the critical value approach, first of all, we have n is equal to 8, HA is mu under 15, so the degrees of freedom is equal to 7. So I'm going to reject HO if t-test is less than minus some value. And we have 0.05 and a one-tailed test at 7 degrees of freedom. That's 1.895. So now, I have stat, test, t-test. I still had to get my hypotheses. And if I'm going to do the critical value, I still have to look this up in the table, when to reject. Stat, test, t-test, input the data. My mu 0 is the 15. If that's less than 15, HO is mu equal to 15. So that mu 0 is the 0, is null. So 15 there. I have my data in list 1. Don't change the frequency thing. Make sure you have less than there and hit calculate. The calculated value of t is minus 1.48. That's not less than minus 1.895, so fail to reject HO. The p-value on your calculator is 0.09. We reject if p-value less than 0.05. Using your calculator, the p-value is equal to 0.09. That's not less than 0.05. Fail to reject HO. Confidence interval, stat, tests, go down to T interval, option 8. And just make sure you have 90%. It still says list 1. Your interval goes from 10.4443 to 15.6. Since this is one mean, we're looking to see if the interval includes 15. Look back to your HO. 15 is in the interval. Therefore, the mean, population mean, might not be less than 15. Of course, you should be able to get this minus 148 and this confidence interval by working them out, but there's some check figures for you in the interpretation. Questions on this? I know I'm moving pretty fast. I'll give you guys some time to write this down. But I wanted to check. Okay, so I think this is the last problem on here. Is this, what kind of problem is this? Two sample t-tests. These are two separate samples. These are type A cars. And these are type B cars. So these are not the same cars. They're different cars. They're different kinds of cars. So this is a two sample t-test. And let's see, we want to know if it says write the hypotheses. I'll just write HA is mu A greater than mu B. Does it have higher gas mileage? It says you can get the statistics on your calculator. So to do that, you're going to put all of those numbers into your calculator. Put all these into list 1 and all these into list 2. Let's go ahead and do that. I'm going to have to erase here because I can't even see the numbers. If I gave you a problem like this with this many numbers in here, I probably would tell you not to do any calculations, just use your calculator to do it. But anyway, just Take a second here. Double check your numbers, make sure you have them in there right. Okay, I think I have mine. So to get the statistics, actually what I'm going to do is, I know if I do either the 2-samp t-test or the 2-samp t-interval, that's going to give me the x bars and the s's anyway. I don't have to just do them through the calc function. So I'm going to do stat tests 2-sample t-test, and I have my data in list 1 and list 2. Don't change the frequency things. I want to know higher than, so I'm going to select greater than. Pooled. There's 2 ways you can go about this. And you're going to have to check it either way. I'm going to select yes that they are pooled, because it looks to me like there's about the same amount of spread in each one of them. If one of those had numbers, like if type B, if that first number were 12 and then it was 43 and that kind of stuff, I would think that's a different variance than the other one. But they look to be in the same range. I could be wrong, but I'm going to select yes. And then I'm going to calculate. And then I'm going to arrow down, and I'm going to see that my standard deviations are 167 and 163. Well, I can tell you this. If I square those 2 numbers, neither one of them is going to be twice the other one. 1.67 is not going to be more than twice 1.63 squared. I'm going to go ahead and write that over here. I might calculate it out in a minute, but I know that neither of those is going to be twice the other. So I guessed right on the yes. So now, I can write down, first of all, the information I have there. X bar A was 32, X bar B 30 point, I'm going to round that to 44. SA was 1.67. SB is equal to 1.63. That SXP is the pooled. Remember, and I'm not going to calculate it now, but when we calculate the pooled variance, we had that 1 over NA plus 1 over NB over here. And then over here we had S squared A NA minus 1 plus S squared B NB minus 1 over NA plus NB minus 2. That's the SXP. Not the, just don't include that part. That's what that is on your calculator. No real reason you need to know that, but that is what it is. Okay, so we do know that the degrees of freedom is going to be NA plus NB minus 2, or looks like, I guess, it says that there are 15 up here, but and then there's no number there. But on my calculator it says I have sample sizes of 16. So I'm going to count these up. I'm going to go ahead and bet that there are 16 of these. So that should be 16 there and 16 there. Yes, there are 16 of each type there. Yeah, and then it also, when I did the output, it has it on there. But yeah, when you do your list thing at each one of them, it has in parentheses the number of item you're on. But I was going to calculate this, and 16 plus 16 minus 2 is equal to 30. And so we're going to reject HO if t-test is greater than some value, and we have one-tailed. Let's assume that this was 0.05. So with 30 degrees of freedom in 05, that would be 1697. That's just off of the t-table with degrees of freedom equal to 30, one-tailed test, and alpha 05. And now on my calculator, I had a t-test of 2.67. Which is greater than 1.697. So we're going to reject HO. Remember, HO and HA, mu A equal to mu B, mu A greater than mu B, because we said higher. So reject HO and say that the mileage is higher for type A than type B. So if you're trying to either advertise what kind of car you want to buy, you can say that type A has higher gas mileage on average than does type B. Now you can decide if you're buying a car, 32 to 30.5, a mile and a half distance. Now you can decide how much that matters to you, or how much that ought to affect your buying decision. Now, if you were advertising based on these results, it would be legitimate to say that the car that you make has better gas mileage than the car that your competitor makes, if you're A and they're B. But just in terms of using that information, I don't know if a difference between 32 and 30.5 about it might be a factor, but there would certainly be other factors that if it were a difference between 45 and 25, that would be a big difference, and I would notice that. Mile and a half, I don't know. But anyway, that's a personal kind of thing. No. Well, it wasn't supposed to. That's supposed to be squared. Let's go ahead. I'm going to go ahead and square those anyway. Well, before I do that, the p-value is 0.006. That is less than 0.05. Therefore, we would reject HO again. And let me go ahead and get the confidence interval now. Stat, test, 2-samp t-interval, option 10 or 0, however you want to interpret that. And let's say we're doing 90%. No, 90%. I know it's not in there. I'm making it up right now. 90%. 0.57 to 2.55. 0.57 to 2.55. In interval doesn't include 0, therefore the mileage is better for type A. And assuming we've picked one of those 95% of intervals that includes the real difference, we think the difference is from about 0.57, about half of mile per gallon, up to maybe 2.5. And again, you could decide if you were purchasing whether or not that's enough to influence your decision. I guess if the car's cost is exactly the same, maybe it would influence my decision. Everything else was equal. But if they differed in price by $10,000, I might just go ahead and eat that half a mile or 2 mile a gallon. I don't know. I don't drive that much anyway, so it's not that big of a deal for me. Confidence interval. Well, I just did that. 5.7. Now let's go and look at those variances. I really don't need to check, but I'm going to. 1.63 squared and 1.67 squared. 2.66. 2.79. Of course, neither of those is twice the other. So we were correct in pooling. Sample size large enough? It's okay if there's skew. And it's based on the 16, not 32. If you had two sample sizes and one of them was 80 and the other one was 16, you look at the 16. Okay? In this case, they're both 16, but it's the 16 that makes a difference. So it's okay if there's skew, not okay if you have outliers or extreme values. And you can check that with box plots here, but that's a pretty limited way to do it. The way you really have to think about that is, I know about my product or what I'm doing. I know that for gas mileage on cars when I'm using the same type, there's going to be some variation, but probably it's going to be a bell curve. Sometimes a little bit more, sometimes a little bit more, occasionally something either a lot more or less. But I wouldn't have much of a problem with someone saying that that's probably a normal population. I suspect that it is. I could be wrong. And if I had a lot more experience testing cars for gas mileage, I would be more and more confident in that. But and even then, skew is okay. I suppose every once in a while a Type A car might get 50 miles per gallon. Have you guys ever heard of that hypermiling stuff? These guys that get like 2 or 3 times the gas mileage of anybody else. Like, they do a lot of coasting. They time themselves. They know how they can get through the stoplights without stopping if they time it right. You know, instead of going 35 miles an hour, some of the times it's 25. Or, you know, their objective is never to stop at a stoplight. They do a lot of coasting down hills and things like that. I've actually tried it a little bit. You can change your gas mileage.